In this video, we're going to help you think through the logic of the problem on the homework. Instead of using the problem as stated, we're going to change the number slightly, but the concepts are still the same. Assume that you have a fair coin. That means that it's a 50-50 chance of getting heads or tails. What is the probability of flipping 5 heads in a row in 5 flips? We're going to change this problem slightly. And instead of using 5 tails in a row in 5 flips, we're going to use 3 tails in a row in 3 flips. And in fact, we're going to use 3 tails in a row everywhere. What is the probability of flipping 3 tails in a row in 3 flips? In order for us to work this out, we need to think about the probability tree. On the first flip, we could get heads or tails. And on the next flip, we could get heads or tails. Now, I could draw the third flip, heads, tails, all the way down, but that would be excessive because I don't really care about what happens after I flip 1 head. I only care about 3 tails. So I'm only going to look at the branch that really matters at this point. Now, we said that this is a fair coin, so that everything has a 50% chance, or a 1/2 chance of happening. So we get a 1/2 here, a 1/2 here, and a 1/2 here. And the path we want is tails, tails, tails. 3 tails in a row in 3 flips. And so the probability of getting tails, tails, tails can be obtained by using the multiplication rule. It's 1/2 times 1/2 times 1/2. We multiply when we're moving left to right down the tree. 1/2 times 1/2 times 1/2 is 1/8. And so the probability of getting 3 tails in a row in 3 flips is 1/8. If 2 people flip a coin 3 times in a row, what is the probability that at least one of them will get 3 tails in a row? In this problem, we want to think about each set of coin tosses as a single outcome. Each person either flips 3 tails in a row or they don't. This follows the miss and match concept that we were using in class. The first person will either miss getting 3 tails in a row, or that person will match getting 3 tails in a row. The same thing applies for the second person. Now, which of these do we want to consider? We want to find the probability that at least one of them will get 3 tails in a row. So we're looking for the probability that at least one match appears on the branches. Working our way from top to bottom, if they both miss, we're not interested in that. But if the first person misses and the second person matches, we do care about this. If the first person matches and the second person misses, we still care about it because the first person got the match and that's what we want. And lastly, if both people match, then we also want that one as well. Notice that we have circled 3 out of the 4 different paths there are. In this situation, we can use the complement to help make our calculation go much more quickly. The probability of at least one person matching is 1 minus the probability of both people missing. And so now we have to think about the probability tree and determine the probability that each person misses. We know from the previous problem that there is a 1/8 chance of a person getting 3 tails in a row in 3 coin flips. This means that there's a 7/8 chance that a person will not get 3 tails in a row. So a 7/8 there and a 7/8 there. And now we use the multiplication rule. 7/8 times 7/8 is the probability that both miss. 1 minus 49 over 64th. Which turns out to be 15/64. And so the probability that at least one person gets 3 tails in a row is 15/64. For part C, how many people would it take to have a 75% chance that someone will flip 3 tails in a row? In order for us to do this problem, we have to extend the ideas from the previous problem. First, we use the complement, that the probability of at least one person flipping 3 tails in a row is 1 minus the probability that nobody gets 3 tails in a row. So we're going to build out a probability tree in that way. We're going to focus only on the misses. The dot, dot, dot just means that this branching action will continue. And we also know from the previous problem that there's a 7/8 chance of missing at each step. The probability of at least one person matching, meaning one person hitting 3 tails in a row, is 1 minus the probability of all missing. By the multiplication property, we know that every new person we insert into this problem simply causes us to multiply by another 7/8, where the number of times 7/8 is multiplied by itself is the number of people. Now, at this point, you need to grab a calculator and do this calculation. You can do it by hand, but it's not very fun. We want the probability that at least one person matches is greater than 75%. If you think about this for a moment, you can see that this would require the product of the 7/8 terms to be smaller than 25%. And what we need to do is we need to look at what 7/8 raised to higher and higher powers is. 7/8 is 0.875, or 87.5%. And we're just going to try raising this to higher and higher powers. So let's square it. That brings us to 76.6%. Raise it to the third power, 67%. If we raise it to the fourth power, we get 58.6%. Now, we don't have to go one by one by one. All we're trying to do is we're trying to find the smallest value that makes this number smaller than 25%. And so let's jump up to 10. That's pretty close. So we're almost there. Let's raise it to the 11th. There we go. So this is smaller than 25%. So the probability of at least one person matching, and by matching we mean having 3 tails in a row, with 11 people, is 1 minus 7/8 to the 11th power, which is 1 minus 0.23, which is 0.77, and that is bigger than 75%. So it takes 11 people. For the last question, how many people would it take to have a 75% chance that 2 people would have the same sequence of 3 coin flips? Notice that this is different. We are not specifying in advance that we want tails, tails, tails to match, but instead that anyone matches with anyone. So let's see what happens. We're going to think about this as adding one person at a time. So when one person flips, there's no way for 2 people to match. So the first result is automatically a miss with just one person. That happens 100% of the time, so I'll put a 1 right there. What happens next? We know that there are 8 possible combinations and that the first person has flipped one of them. We don't know which one, but we know he's flipped one of them. That means that the next person has a 1 in 8 chance of matching him. And so that means that there must be a 7 out of 8 chance of missing. Now this next step requires a little bit of thinking. If the first 2 people have already flipped and they are not matching, that means they have 2 different combinations. This only leaves 6 possible combinations for the next person to get a miss. At the next step, if the first 3 people have missed, it means they have 3 different combinations, leaving only 5 out of 8 ways for this person to miss. And so we can see the pattern. For the next person, there will be 4 out of 8, and then 3 out of 8, and then 2 out of 8. And so we need to relate this probability tree to the calculation that we're interested in. How many people would it take to have a 75% chance that 2 people would have the same sequence of 3 coin flips? Probability of some match. Again, using complements, this is 1 minus the probability of everyone missing. The multiplication rule says that we multiply these values together, and we have as many terms there as we have people. And so what I'm going to do is I'm going to make a chart. I'm just going to start filling it out. So 1, 2, 3, 4, 5, 6. If we have only one person, then there's no way for two people to match. So probability of matching is 0. And we can see this by looking at the formula that we have. If we only use the first term, 1 minus 1 is 0. With two people, we have 1 minus 1 times 7/8, which is 12.5%. If we have three people, it's 1 minus 1 times 7/8 times 6/8, which is about 34.4%. If we put in a fourth person, it's 1 times 7/8 times 6/8 times 5/8, which is 59%. If we had in a fifth person, 1 minus 1 times 7/8 times 6/8 times 5/8 times 4/8. And that turns out to be 79.5%. Notice how small this is relative to the other problem. In the other problem, when we specified the combination in advance, it took 11 people to have a 75% chance of getting a match. But notice that if we just looked for anyone to match, it took 5 people to have a 75% chance of matching. That's less than half the number of people we needed when we specified in advance. The concept here is exactly the same as the birthday paradox. For the birthday paradox, it takes very few people for someone to match. But if you specify the birthday in advance, it takes a very large number of people.